Hello everyone. Since I was unable to do a review session, a finals review session for you guys, I've decided to make somewhat of a problem walkthrough video where you can kind of see a way to approach these problems. And the way I'm going to do this is essentially I'm going to talk through the problems in a pretty quick pace. And what I want you to do is the first time you watch this, or if you plan to watch it more than once, I'm not sure, but the first time you watch this, don't try to write stuff down because the video will always be there. Just watch and listen and try to incorporate the type of thought process in terms of how you approach these problems. What I want to do is I really want to try to focus on the patterns you look for, especially in synthesis, to try to figure out, okay, where do we need to go? So, having said that, I'll go ahead and get started pretty quickly. Now, here what I have is I want to figure out how we're going to get from this alkene to this compound over here. And it's a little bit difficult, but one thing we can focus on is the type of patterns we see in the product. Specifically here and here, I have a hydroxy group one away from a alkyl halide, and that makes me think that, okay, we probably had a halohydrogen formation, because that allows us to add both an methoxy or hydroxy group as well as an alkyl halide. So now the question becomes, what are reagents going to be? We should be aware that the first thing we'll need for sure is going to be the Br2. That's going to form our bridge when we actually react with the double bond. Now for the other part, the fact that we have this ethoxy group is we need to consider, okay, if we're adding that to the molecule, it has to be in the reagent somewhere. In this case, all we need to do is just add the hydrogen to actually make the ethanol. So that would actually do what we want. So the first step we get is after the bromine reacts to the double bond, we get the bromium bridge that we'd expect, the positive charge on the bromine, and excuse the poor handwriting. After that, our nucleophile is going to be that ethanol that's going to come in and attack at the more substituted position. Now keep in mind, that does happen when you have the bromium bridge. In other ones where we don't have something like water or ethanol, the other bromine just comes in and attacks, and you don't see it attacking a specific position because the same thing was added on each side. In this case, after the attack, you'll eventually deprotonate and get this as your product. So the main pattern to recognize here is that we had a halide and an ethanol group one away from each other. And since we had the double bond to begin with in the product, and we had no real change in the number of carbons, we can go ahead and assume, okay, we're doing a halohydrogen formation. So we'll move on to the next one. One of the first things you want to do when you look at a reaction is to see if the carbon skeleton is changing. Is the number of carbons changing? Over here on the left we have 3 carbons, while over on the right we have 6. 1, 2, 3, 4, 5, 6. See, even for me, I have to make sure that I'm counting all the time because it's easy to miss carbons. Considering that, we know that we've created a carbon-carbon bond. And when we think carbon-carbon bond, what should come to mind immediately is some sort of Grignard reaction. And to do that, we're going to need 2 things. We're going to need something at the bottom right, if I can, something probably that has a carbonyl group that we can attack. And then we're going to need something that has the Grignard reagent, or the MgBr. And that's what we're looking to create with what we have. So considering this, when you look at the product, you want to think, okay, what about the product over here came from what we had in the starting material? Now, considering the way this is drawn out, it looks like this part came from our starting material. And that's a pretty good hypothesis to work off of. And the thing is, considering that we need a double bond to oxygen, we could probably make this into our electrophile, the thing we attack with the Grignard reagent. But to do that, I'm going to need a double bond, which means we're going to have to oxidize that primary alcohol to an aldehyde. And to actually stop at the aldehyde, we're going to have to use PCC. Because remember, that allows us to, with a primary alcohol, to go to the aldehyde and stop. Otherwise, with dichromate, we go all the way to the carboxylic acid. Finally, this gets us what we want in terms of having this double bond that we can attack. Now the question becomes, well, what do we want to add? Well, we already have 3 carbons over here. 1, 2, 3. And we're adding another chain of 3 carbons. So the Grignard reagent we want to add is going to be 1, 2, 3 carbons, and then the Grignard part, you might say, the Grignard reagent. And you can just add it as it is. You don't necessarily have to show that you're making it. Which, when you do that, you would expect to get the attack right here, pushing the electrons up onto the oxygen, and that would put a negative charge in the oxygen. So you have to make sure that you follow it up with a little bit of just dilute acid or hydronium to eventually protonate, and that'll help you get to your product that you want. So once again, the key point here is recognizing what the starting material is part of in the product, which we decided was this part. The fact that we created a carbon-carbon bond right here, which means that we need a Grignard reagent. And since we know we need a Grignard reagent, that means we need to be considering how are we going to get these functional groups that are required to do a Grignard reaction. The reason I made one like this, on the left of the starting material where we only have just carbons and no functional groups, is that you're going to have to figure out a way to functionalize something on this molecule. Because the way it is, we don't have anything that we could substitute. We really don't know how to add stuff to a benzene ring yet. We don't have anything we can eliminate. So the idea becomes, well, how do we functionalize stuff that's just made of carbons? When you deal with something like that, where you have carbons and nothing's on it, you want to think of some type of radical bromination. In this case, since we have a allylic position right here, and if you look here, we're actually adding a functional group right here on this last carbon. What would be perfect for this would be NBS and light. And the reason I bring up NBS is because it allows us to specifically add to an allylic position, or a bromine to the allylic position, without disturbing double bonds. Because if we had something like Br2 in light, and we had a double bond in our molecule, well, we could get a halogenation. We'd form the bridge, the bromium bridge. So we can't really do that in a lot of cases. This works really well because now we functionalize this position right here. And if we look over here, okay, we're just replacing this bromine with this thiol group. So all we need to do is add a good nucleophile, which in this case we could just add NaSH, which would have a negative charge in the sulfur. So if I went ahead and drew that in, well, we just get a normal SN2 attack, kick off our leaving group, the bromine, and that would get us to our product. So here the main focus was looking at how do we functionalize carbons that don't have any functional groups to begin with. And when you see occasions like that, you want to be thinking of radical bromination because it allows you to actually start doing something. Because once you add a bromine, you can substitute like we did here. You can eliminate. You can do a lot of different things. This one's a bit tricky, and I want to focus on how we can identify patterns in molecules, not only based on where the functional groups are located, but also the stereochemistry. So let's look over at the product on our right over here. We notice that we have an indicated stereochemistry, specifically a hydroxy group that's on a wedge and a methyl group that's on a hash. To make it a little more clear, I'm going to draw the hydrogen that we don't see that is on the wedge. Now, considering here the OH and the hydrogen are on the same side, they essentially could have been added in a syn addition. And considering that the hydrogen and the hydroxy group together form water, you should be thinking, okay, maybe we did a hydration here that we ended up adding on the same side. The other thing to notice here is that the oxygen, when it was added, so we're already thinking addition, right? And when we think addition, we think, okay, we need a double bond to actually do an addition. The other thing to notice, as I was mentioning, is that we have the OH. It was added to a least substituted position, and that'll be more clear when we draw where we thought the double bond was. So actually, let's kind of work back from this. Let's say we did assume that we did a hydration, and we need to think, okay, if we're doing an addition, and we're adding this OH, well, what do we need to start with? That would be a double bond. You need a double bond to do these additions. So we have all the carbons we'd expect, as before. We can't add carbons through additions in the way that we think with a double bond, only Grignard reagent. Well, if I have here, the question becomes, where in the world are we going to put the double bond on this molecule? If we look back at our product, we have the OH here and the H here, which means that the double bond would have to be between them. And when we do that, we get the double bond we need. Then the question becomes, well, how do we form a double bond in the first place? Now it should be pretty clear as we look at our starting material. Well, one way we can get a double bond is to do an elimination. So now that we know the path we're going to get to the product, all we have to do is fill in the reagents. Starting from the top, if we're going to do elimination, we're going to be needing a base. And the question becomes, do we want a big base or a small base? Well, our two choices for abstracting the hydrogen are here and here. And since we have the double bond forming at a more substituted double bond, then we're going to want to go ahead and use a normal or small base so we get the thermodynamically favorable product. Otherwise, we take out the other hydrogen and get the different product. So now that we have that, just a strong base, that's sodium methoxide, we need to think, how do we go from the double bond we have right here and add this, do the hydration, add the H and the OH? Well, once again, we notice that the OH is added to the less substituted position, which would be anti-Markovnikov position. So that means that what you want to think of is if we're adding that OH to a less substituted position on the alkene, then you want to be thinking of hydroboration oxidation. So the best way to kind of learn these reagents is to learn the function they are. So instead of trying to learn what a screwdriver is and what it looks like, learning what it does, that actually drives screws into a piece of wood, for example. And then it gets easier to memorize because you have a meaning for all of your reagents that you're using. And then, so you have the products, and then we're done. So once again, it's all about pattern recognition, because we noticed that we had a pattern over here in terms of having the OH and the H and a syn addition, because that's what hydroboration oxidation does. The other part, what it's noticing, that the OH was added to a less substituted position, a secondary, versus this tertiary position over here. And these hints drive you to the conclusion that it had to come from a double bond we got here. Which, from there, you ask, how do we form double bonds? Elimination would be perfect for doing that. Every once in a while, you run into questions that have special reactions in a way, they don't see too often as compared to elimination and substitution. And this is one of them. This is where product recognition does come in handy. Because on the right in our product, we can notice that, we form this disulfide bond. And really, there's only one way that you've learned to form that. And it's going to involve essentially coupling two SH groups together. Knowing that allows us to focus on what we use to make the product and the fact that these are the two things we coupled. We have identical groups with the sulfur that we coupled to make this bond. So if we consider that, we can, without thinking about the reagents, we can work backward and say, we created our molecule with a coupling through this. Now, the question gives us the stipulation that we need to start from an alkyl halide. And right now we only have the thiol group on the carbons we want. We don't want to change any of the carbons, so we can go ahead and put these three carbons. And in terms of the alkyl halide, well, let's just go ahead and put it on the same position. We could easily do a substitution here because thiols, or the sulfur, is very polarizable, which makes it a great nucleophile in terms of actually attacking something. Now that we know the path we're going to get there, let's fill in the specific details we use to accomplish each transformation. Well, we know for the first one, we just go ahead and do a substitution. So add a good nucleophile with the NaSH. That will get us, if I go ahead and draw the mechanism a bit, nice SO2 mechanism because it's a pretty good nucleophile. Even though it is secondary, you could even choose the solvent to make it more SN2. That gets us this product, and then it comes to all we need to do is do the coupling, which you just want to know the reagents for that. It's the bromine gas, the sodium hydroxide, and water. And that's one that you shouldn't worry about too much. It's more about recognizing this is a very special case, and this special case is going to require these set of reagents. Since it stands out so much, you can start to develop a pretty good familiarity with realizing, we have the disulfide bond right here. That's going to involve something with Br and a base, sodium hydroxide, and kind of get you really into the right direction. With this one, this is going to be a good way to practice looking at what carbons in our product came from the starting material. Because the way this is right now, we have a pretty large transformation. We're going from a cycloalkane that has no functional groups whatsoever to this chain that isn't cyclic, that has these two OH groups. And the question becomes, numbering your carbons can be pretty useful in this regard. So over here on the left we have 6. On the right we want to look for any certain patterns of 6 that would help us out. And what I'm seeing is that, well, let's see how far away these two OH groups are. We have 1, 2, 3, 4, 5, 6. They're 6 away, which means that I'm willing to bet that those 6 are what came from our starting material, and that these methyl groups were added somehow. And keep in mind that that's a 1 over there, just to make sure. So we probably added those methyl groups right there, which means if it's a carbon-carbon bond, then we used a Grignard reagent. So let's actually kind of work backward from there. So to have a Grignard reagent, as we saw before, we need typically something like a double bonded carbonyl group and the MGBR that's going to carry the carbon group we want to add that'll act as a nucleophile. Well, if we were to remove those two methyl groups, I draw the 6-member chain, 1, 2, 3, 4, 5, 6, that we started with. Well, you'd expect to see that our double bonds right here and right here are carbonyl groups. And they'd just be aldehydes because we haven't added the carbon yet. Well, that works pretty well, and that would just make our Grignard reagent CH3MgBr. So at least we know the roles that each of these molecules are playing. We know the players in the reaction. Now the question becomes, how in the world are we going to get from this cyclic alkane to this chain over here? And it's going to require that we're going to have to break a bond. There's no doubt about that. And breaking a bond, that's very rare in organic chemistry. And it should bring to mind that we're going to use something like ozonolysis, which requires a double bond. Since we know it requires a double bond, we need to put a double bond somewhere on this. Well, it has nothing to begin with, so we need to functionalize it, and that's going to require what we mentioned before, using something like Br2 and light. What all that'll allow us to do is at least add one bromine group somewhere right here. And it's going to probably do it once, and all the positions are the same, so you're not having a problem with selectivity. Once we do that, how do we create a double bond? Well, we're just going to eliminate, which would form our double bond somewhere on the ring. Keep in mind that if all we need is a base, so I can go in there and fill that out. Even though I'm filling in the reagents as I go, the important thing is to realize the path you're taking and then realizing how you get there. Because if you try to focus on knowing all these reagents at first, it's going to be overwhelming. Now we have the link, or the missing link, is how do we go from here to here? Well, it involves breaking this double bond, breaking the bonds between these carbons completely. And as I mentioned before, that's where ozonolysis comes in. Given the name, it's probably going to involve ozone, and then we're going to have some reducing agent. Typically, it's something like DMS. What I would do is I would associate the DMS with the ozone. Don't think of, when I say reducing agent, I don't mean to mislead you and make you think of LAH, or sodium borohydride. Just associate these two as being, as a group, a tool group that allows you to break the double bond. And when it breaks the double bond, you see it goes, we still have the 6 carbons that go to the chain, and it replaces where the double bond was with these carbonyl groups, which are perfect for doing the Grignard reaction. So to complete the steps, or the reagents over on the right for the product. Since we do it on both sides, the Grignard reagent, let's go ahead and add an excess of the Grignard reagent. And then we know that when we push these electrons up, thanks to the attack, we're going to need to protonate afterwards. So we can just add some acidic water, and that'll get the transformation we're looking for. So here, once again, we're looking at how do we figure out where our starting material comes into play in regard to the product. Where does it exist now? Where is its new home? And counting carbons can really help you out with that. Once you do that, you find one thing, and you kind of find a pattern, and you start to work backwards. And a lot of these mechanisms, what we've been doing, we've been kind of meeting in the middle. There's no reason to go from the back and all the way backwards, or from the front and go all the way forwards. You can meet in the middle, and you'd still be able to draw the synthesis and the retrosynthesis without any problem. You'll notice that this compound comes directly from your sample final. The reason I chose it is that I wanted to illustrate a thought process, or the thought process you can use to approach this. Keep in mind there are a few different ways to approach this, so if it doesn't exactly match up with what I'm going through, don't let that concern you. In any case, this question requires us to figure out how to form this molecule using 5 carbons or less. When I see these problems that limit us in terms of the number of carbons we can use, I try to figure out what chunks we put together, what tinker toys and chunks that we put together to get our product. So I'm looking here, I want to see if I can add the biggest chunks I can find, and right here I see that we have, a nice 5 carbon chain and a 3 carbon chain. I'm willing to bet that those are the chunks we're going to be putting together, which means that the bond that we're breaking when we do the retrosynthesis, or the bond that we're forming, either way, is going to be this bond right here. I know it's hard to see, but we're going to be cutting that double bond when we go backwards. So I know to get to this, one thing I want to consider is we have a double bond, and if I'm going a step backwards, I have to ask, how do we form that double bond? Well, it's going to be some sort of elimination. And considering that we know that we're forming a carbon-carbon bond, which means that we're going to be having a Grignard reagent, I'd probably want to eliminate an hydroxy group, because hydroxy groups are typically left over after a Grignard reagent. So here what I'll do is I'll just say that we'll go backwards one step. I have all the carbons, because I haven't created the carbon-carbon bond or broken it. So we'll go ahead and say I put the OH right here. And the important thing to realize is that in terms of choosing where we had a leaving group, it has to touch where the double bond used to be. And our double bond used to be right here, so we fit that requirement. The OH is right over on the least substituted site, and that's fine. Now that we've done that, once again, we still know that this is the bond we wanted to break when it comes to forming the carbon-carbon bond. Once again, what we need for the Grignard reagent, and what you're looking to see, is some sort of carbonyl group typically. At other times it can be an epoxide, just to make sure I'm not making an always or never argument. And then we need something that it has the Grignard reagent. Let's look at our chunks again. We have this chunk and this chunk. Whatever has your hydroxy group after the Grignard reagent, that's what's going to be the carbonyl group beforehand. Whatever else, the other part, what we have here, that's going to be what your Grignard reagent was. So what we can do is there are a few ways to do this. If I go ahead and draw my carbonyl group, and it has 3 carbons, so 1, 2, 3, just being an aldehyde. Then, once we have that, we know what we can add to it. Is going to be in the first step, we're going to have the Grignard reagent, which will have 1, 2, 3, 4, 5 carbons, and then MgBr. Of course, you'll have to follow that up with some acidic water, as you've seen before, just to make sure you protonate the negative oxygen you create after the attack. So if I just draw this attack real quick, mechanism, get that, you protonate, and then you get this. So now we've fit all the stipulations in terms of having no more than 5 carbons. And from there, we could go back farther and say they were trying to make this or this, but really there's no need to. We fit all of the requirements of the question, and we can go on. Here, the idea, once again, was trying to figure out what was the precursor to parts of the product, and we divide it into chunks. And there are a few different ways you can do this, but this is a way to illustrate a way you can approach it. The last 2 problems I have in this video are more conceptual and less regarding synthesis. I want to capture some concerns when it comes to elimination, and then this last one at the end will be about radical mechanisms, and I just want to go over some other steps besides synthesis. Here we know that, we have something that's going to act as a strong base right here, and we have leaving groups that we could use, so we would expect to have an elimination. However, keep in mind, you want to consider that elimination, E2 in this case, since we have this strong base, it's going to require that we have the leaving group and the beta proton that we abstract, the beta hydrogen, to be anti-paraplanar. Since we have a ring here, that kind of creates some concerns that we might have. Let's look at this chlorine, for example. It's above the ring. And in order to eliminate it, we need to find beta hydrogens that are below the ring, that are going to can be anti-paraplanar to it. Let me go ahead and draw the beta hydrogens in relation to chlorine. We have one right here on a wedge and another right here on a wedge. Neither of these can be, since they're above the ring with chlorine, they can't be anti-paraplanar to chlorine, which means that we can't really eliminate this chlorine right here because we don't have the necessary part of a beta hydrogen to abstract in order to get the reaction to go. Over here, though, we actually have two hydrogens on each of these carbons for the bromine compared to the bromine, and they're the same. And that means that one hydrogen is going to be on top and one's going to be on the bottom, which means we have no restriction in terms of actually getting this eliminated because we do have a hydrogen that's anti-paraplanar to our leaving group. So we could actually abstract that. These electrons would go here to form the double bond and kick off the hydrogen, and your product would look like this. The reason it looks like a weird product is because we actually didn't touch one of the leaving groups. The reason being that we didn't have an anti-paraplanar hydrogen to abstract. So this is the product you would get. All I wanted to do here was focus on the fact that with elimination and with other reactions, there are conceptual parts that play an important role in the reaction. In this case, it's the anti-paraplanality, which isn't a word, between the beta proton and your leaving group. You'll notice that this one also comes straight from your sample final. And once again, I just wanted to give an easier way to think about radical mechanisms because I've seen some concerns from certain students about, for example, how do I know I have all the propagation mechanisms? And the way you want to approach this is consider having a better idea of what is initiation, what is propagation, what is termination. How is there a better way we can actually describe how these are happening? And let's start with initiation, and I'll just put NI as the abbreviation. Typically, what is acting as your initiation step is going to be what you're adding to the reaction, because radicals aren't a normal part of nature. Well, they occur, but they don't happen too often. So typically you need to add something to initiate the reaction. A lot of these are things like hydroxide, or in this case, bromine, which has a single bond between two of the same electronegative atoms. What happens is we have the homolytic cleavage, which allows us to split directly those two bonds in the bond, electrons in the bond, to create these bromine radicals. And there are two of them, right here, and then same thing here. What to notice here is in an initiation step, we start with 0 radicals and end up with 2. Or another way to look at it is we start with 0 radicals and we end up with radicals. In terms of the algebra, that's how it kind of works. Propagation, on the other hand, we're going to be saving a radical. We're going to be conserving the radical. So within the halogenation, we typically have this hydrogen abstraction step. And a lot of these radical mechanisms do involve 3 single barbed arrows, you'll notice. So let's look here. So we have a hydrogen from the bond meeting with the bromine to actually form a bond, and then the other guy falling back onto the carbon. The result is we're creating a carbon radical and the HBr. Notice that we start with 1 radical and we end up with 1 radical. So the radical is conserved, and in propagation steps the radical will be conserved. So that leaves us with another one if I move down a bit, or move things up a bit, is now we have a new radical that we can work with, and if I draw this carbon radical, another way to propagate it is having it react with another Br2 group. Once again, we're going to see 3 arrows. We're going to see a bond form between bromine and the carbon radical, and then another one that goes back onto the bromine. The result is we'd expect to have the same radical on the right side, just as we had the 1 radical on the left side. We have this right here, plus another bromine radical. So once again, we conserve the radical. Notice here that we create the product that we're wanting to create in terms of the halogenation, even though it isn't a termination step. Just because we form in the propagation step doesn't mean it can't be the termination step, because we're focusing, when it comes to initiation, propagation, and termination, we're focusing on are radicals made, or are they consumed, or are they conserved? That's what we're really concerned with. So once again, if I move some of this up, and I know it's kind of getting crowded, my bad. Move that up. I know it's messy. For the termination, we're looking for things that go from having radicals to no radicals. And let's look at the one you do when you actually form your product through a termination. You have the bromine radical and the carbon radical. These two radicals just couple together to form the product that you want. Which means if you look at kind of the electron algebra, we go from 2 electrons to 0 electrons. Hence the word termination, because we are taking care of radicals in the system. In terms of the concern of how do you make sure I have enough propagation steps, don't let that override your thinking. The way you want to approach it is, I would say this: recognize that initiation, propagation, and termination are making radicals, conserving radicals, and getting rid of radicals respectively. From there, all you have to consider is, what radicals can I work with? The main radicals you work with in this mechanism are going to be the carbon radical. Oops. Just ignore that. All right, the carbon radical and the bromine radical. And you're considering, okay, what can I do? How can I react these radicals with the other players in the reaction, which would be Br2, the alkane, and that's pretty much it. So you're just kind of coupling these together and see, how can I get this to work? It's more about thinking about the electron algebra than trying to figure out, did I get everything? Well, that concludes about everything I had for a quick walkthrough video. If you have any questions, feel free to send me an email, and I hope this is actually helpful for you. So good luck on the test tomorrow.